The first part of this next unit is about light and how light can act like a wave. People have known light does bizarre things as it gets sent through small openings, as it gets sent through glass, as it gets sent through into a mirror. They've known that for a long time. And eventually it was figured out that this could be explained if we thought of light as a wave. The first thing we're really going to look at is what's known as an interference pattern. And I'll give you an example. This thing in front of me has two very small slits, about 1/4 millimeter apart. If I shine laser light through them like that, it makes a pattern on the chalkboard that's behind the camera you're watching. Let's look at that pattern. In order to understand this, we have to go back and look a little bit at how waves act. So I'm going to leave this classroom for a minute and go to the beach, and we'll see if we can explain the pattern we just saw using water waves. I'm down here at the beach and I've got my feet dipped in the water. And I'm just going to start splashing like this with one foot. Let's watch the waves as they go away from me. As you can see, they're circular. If I stop with this foot and switch to the other, if we look out, we see it as we get far away, there's not much difference in the waves caused by my first foot and my second. My feet are pretty close together. But something kind of amazing happens when I stop and then start doing both feet. As we go away, you start to see places where the waves are big, and you start to see places where the waves seem to almost be canceled out. This is because of the waves coming from my 2 feet interacting with each other. Sometimes they're acting constructively, sometimes they're interacting destructively. So I thought it might help if I showed on the film a line where I think the destructive interference is. It's actually easier to see when the waves are moving, but I'm going to put in some red lines where I think there are areas of destructive interference. And you can see in these areas where the red lines are, the waves just aren't as big. And that's where the waves from one foot are canceling out the waves from the other foot. And in between them, the waves are actually bigger than they are anywhere else. So those are areas here, 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 that I would call constructive interference. This is called an interference pattern. And anytime you have two sources of a wave, you see it. So it's actually a good way to check for waves, to see if the phenomenon you're experiencing is a wave. In a classroom, we can have two speakers, each playing the same note, and we can walk around and find places where that note is loud and where it's quiet. If you have a laser beam going through two slits, you actually see light in places where the light gets brighter and where it totally disappears. So those types of interference patterns are how we can tell that something actually is a wave. Let's take a look at the light going through two small slits. So if you do that, you get something that looks like this. And if you zoom in carefully, you could see a pattern that's actually very much like what we saw with the water waves. Now, if you're not seeing that, keep in mind that we're only seeing where these waves are incident on this black backsplash. Imagine if we drew a line across those water waves. So like this. That's what the backsplash is doing. It's cutting across it horizontally. And you can see that we're seeing places where there's constructive interference, destructive, constructive, destructive, constructive, destructive, etc. There had been a lot of debate up until around the year 1800 whether light was a particle or a wave. And one of the people who got strong evidence that it could act as a wave was a man named Thomas Young, who first did this experiment in 1801. Young said this is why we're seeing the interference pattern we are, because like the water waves, light is traveling as a wave.
Ironically, we now know that both theories are sort of true. Light is both a particle and a wave, and we'll get into that more later. So what I want to do now is I want to talk a little more about the geometry that leads to having constructive and destructive interference at a certain point. And then we'll see if we can come up with any equations to determine where those points will be based on angles and wavelength of light and distance and such.
All right, so what we're going to try to do is figure out why in some places it seemed like the waves were interfering constructively. In other words, they were really big. And in other places they were interfering destructively. In other words, they almost didn't seem to be there. I've got my 2 feet dipping into the water. I've got an imaginary line running through the water. And we're going to check 2 points along this line. One up here, one down here. And we're going to see if in those locations is there constructive or destructive interference. So first thing first, we draw a line directly connecting each leg and a point. So this first one, my left leg to this point, I'm going to mark off every 4 centimeters just to make sure I've got my wavelengths accurate. These are going to be 4 centimeters per half wavelengths, so the wavelength will be 8 centimeters. All right. So there's one of them done. I use a different color connecting my right leg. All right, so now we'll just start drawing a wave. Now obviously I can't draw the real wave which goes in and out of the board. And I also am only going to draw a sine wave, and I think real waves have more complex shape than that. But this will at least give us some idea of what's happening. So, okay. Now let's do the wave coming from the other foot. Notice they start in phase, but they end up out of phase. So this is destructive interference. The peaks and valleys are overlapping with each other. These waves are tugging the water molecules in opposite directions. Let's count how many complete wavelengths. So this is one wavelength. Let's see how many we get for both the distance from my left foot and my right foot to this particular point. So that's 1, 2, 3, 4. That's 12 wavelengths. Let's do the other one now. 9, 10, 11 and a half. So we got 12 wavelengths on this one and 11.5 wavelengths on this one.
So we're going to see that that extra half wavelength on one of the distances is characteristic of destructive interference. If one wave had to travel a delta r, change in distance of a half wavelength longer, that takes things that were in phase and puts them out of phase. So basically one wave's trying to tug it one way and the other's trying to tug it the other way. So that explains our destructive interference. Let's look at one that leads to constructive interference now.
So we'll start the same way. We'll draw a line connecting this point to each foot. Now the right one. All right, so let's check these waves. All right, so there's that guy. Now we'll do from the left foot. So you can see that when we reach the wall here, we're basically in phase with each other. So this is constructive interference. We expect really big waves and really big valleys here. So let's count how many complete wavelengths we had in this case. So from my left foot, basically 12. 12 and a quarter. And let's look down here. 10, 11 and a quarter.
So just to summarize, what makes something have destructive interference is if the difference in path lengths, in other words, the difference between how far each of the waves had to travel, is a half number of wavelengths, you get destructive interference, or any multiple of the half number. If it's any multiple of the whole number of wavelengths, you get constructive interference. To help you see what was going on with the waves in this example, I used a couple of tricks. I drew the peaks and valleys of the water wave as basically this sine wave here. So that represents something that's real. I also drew a line representing the direction it moved. That's not really there, but drawing such a line on top of real waves is actually a really valuable way to simplify a diagram and see where those waves are traveling. We won't draw a lot of sine waves like this, but this idea of a ray, the direction of motion of a wave, we're going to use a lot. Let's try to draw such rays on top of the water waves that we saw in this example.
But let's watch the waves as they go away from me. As you can see, they're circular.
So we can see the peaks and valleys on these waves, but it's kind of confusing if we're trying to figure out the direction they're heading. So if we had something that represented that direction at every point, that could be helpful. So here's how we do that. We draw these rays in, and if you look at the ray, it's always perpendicular to the peaks and valleys. I did it as perpendicular as I could. And it's basically just pointing in the direction that the thing is actually moving. So once we draw these rays, we can symbolize this wave by these lines here, and then we don't have to actually draw all the peaks and valleys in. That makes diagrams a lot less confusing. This is a point source. My foot was bobbing up and down, and the waves were spreading out as circles. Let's take a look when what happens when we change a point source to something else. I've replaced the vibrating point source now with a vibrating bar. And as you can see, it makes long flat waves that go from the top of the screen down towards the bottom. So we could draw a ray as basically perpendicular to all of these. And that ray will represent the wave of light for us. Notice that other rays we draw essentially are parallel to this. And that's one thing about light coming from a distant point source. The waves are essentially flat, and therefore the rays of light we could draw are essentially parallel to them. So we're going to make that assumption as we look at the light waves generated by the laser beams in the upcoming examples. I'm just going to draw these rays, but what you should understand is that there's waves of light running perpendicular to them. So we're going to use that ray model of light to track where individual pieces of the light wave coming out of laser beams goes. And we'll try to use our understanding of how waves overlap with each other and that ray model to explain why we get a diffraction pattern like this. Also, there's spacing here. Is there anything encoded in that spacing that's important that we could find out about? So our first experiments are going to involve shining laser light, which is coherent. The wavelengths are in sync, like the waves coming from my feet were in the previous video. We're going to shine that light on a pair of small slits, and we're going to allow the waves coming from those slits to diffract, just like the water waves. And we're going to examine the pattern on a screen that's farther back. We're going to do this with different colors of lasers to see if there's any information encoded in the pattern we see. So I was able to perform that experiment with 3 different colors of laser. A red laser, which has a wavelength of 650 nanometers, a green, which has a wavelength of 532 nanometers, and a violet that has a wavelength of 405 nanometers. So apparently the spacing of the bright constructive interference places depends on the wavelength of light.
How does that work? Well, I've got two waves coming in phase, and they're coming to a maximum at this point. And if they're at a maximum at this point, we know there's probably several other maximums evenly spaced up and down this wall. Why are there different ones? Because for these to arrive in phase, they have to be offset by a certain integral number of wavelengths so that the peaks and valleys line up in the same place. If you have any sort of fractional wavelength, the peaks and valleys won't line up, and that will give you destructive interference. So let's take a look at this example here for this maximum. What's the path length difference between how much farther the bottom wave had to go than the top one? Well, this is kind of an exaggeration here. In reality, this is so much farther away. Remember, these were only 1/4 millimeter apart, and I shot it all the way across the classroom. We could basically say that these two rays were parallel. And if they were parallel, we could say that this is approximately a right angle. Now, if these are a distance d apart, that's the hypotenuse of this right triangle. So what's the path length difference here? Well, if that angle is theta, that side is d sine theta. So that's where we get the idea that d sine theta, the path length difference, has to be equal to an integral number of wavelengths. So some number m, I don't know which it is, times the wavelength of light. So this directly relates the distance in the slits to the wavelength. You can get m by counting the number of fringes from whatever the central fringe is. And the only thing you need to know is the angle, theta. So I've drawn that here. That's not going to be something that's going to be easy to see in an actual experiment. But it turns out that that's also this angle. The angle from the slits to whatever dot we're looking at. And to prove that, just imagine that this line carried on through like this. Again, we're approximating this as a right triangle because it essentially is, if this is really a lot farther, that makes this a right angle too. And also this is clearly a right angle. So if this is the complement of theta, 90 minus theta, then this here must be theta. So at the end of the day, by making measurements of the interference pattern, we can figure out what wavelength is.
So we're not going to spend a huge amount of time doing labs with double slit diffraction, because as you can see, the interference fringes are very close together, and our ability to measure them in class without much error is going to be pretty low. But it turns out there's another type of optic called a diffraction grating that has many slits, not just a few. And these produce an interference pattern that's a little easier to measure. And that's what we'll spend most of our time in class playing with. Let's take a look at a diffraction grating. This is how we'll run our experiment with the diffraction grating. It's mounted on a pair of rulers, and I've got them at the same distance on each ruler, so we know it's perpendicular to the wall. And we're going to aim our central fringe right at the top of the ruler. So our central fringe in each diffraction pattern will be 8 centimeters. And we'll measure how far away the first bright fringe is from 8. The diffraction grating is in this old 35 millimeter slide. It's 30 centimeters from the wall. And basically this diffraction grating has thousands of microscopic slits directly next to each other. So here's a microscopic model of a diffraction grating. And when you shine coherent light through the diffraction grating, on a screen far away you get interference. And you get constructive interference at certain places. Now, this is all monochromatic coherent light. I drew the lines in different colors just to make it easy to see what's happening. At each spot where you get a bright fringe, you're getting constructive interference from many, many, many rays of light coming from different slits. So this is trying to show that at this spot we're getting constructive interference from all 4 labeled slits. Same here, same here. And you have darkness in the spaces between them. That's places where you do not get constructive interference. Let's try to figure out why. So this picture represents several slits in a diffraction grating. Just like in 2 slits, the distance between consecutive slits has a distance d, and since the screen is so very far away, we can assume that the light leaving one gap and the other gap and going to a point on the screen is essentially parallel. Well, the path length difference between them is going to be d sine theta like it was before, and we'll get constructive interference between these 2 rays if that's an integer number of wavelengths. In other words, if d sine theta equals m lambda. But check this out. We can also have constructive interference between slits that are not next to each other, like maybe this one and this one. Well, in this case, the distance between them is 4d. And if the rays of light are going to the same spot on the screen, their path length difference will be 4d sine theta. So in this case, 4d sine theta must be m lambda. And here's the catch. If this is true, so is this, just from a different value of m. So if you get constructive interference from a consecutive pair of slits for a certain wavelength, you're going to get constructive interference from lots of slits. And that's going to leave bright fringes on the screen. Let's see what those look like in real life. And I'm going to try the lasers one by one. And I'm basically going to measure how far away, using this ruler, the first fringe is from the central. So I'm going to start with red, and I'm going to use the spacing of the red to determine the distance between slits in this diffraction grating. I'm then going to verify that by using the green and blue lasers, and based on how far away they're spaced, trying to come up with a prediction for what their wavelength should be. Since we know their wavelengths, we can check that. So I used the red laser whose wavelength I know is 650 nanometers, and I used the equation for spacing of bright lines with a diffraction grating. I'm using this to basically solve for what's the spacing between the slits in this diffraction grating. So I went to the first fringe. It was 11 centimeters away from the central, and I was able to calculate that it must be 1.77 times 10 to the negative 6 meters. What we're now going to do is we're going to use the green laser and the blue laser. We're going to see what their spacing is, and we'll see if this is an accurate number, because if it is, we should be able to predict what the wavelength of the green and blue laser is. All right, so here's green. Notice it's significantly closer. All right, so same calculation as before, d sine theta equals m lambda. The only difference now is we're going to use our calculated value of slit separation that we got with the red laser, and we're going to solve for wavelength. So for the green laser, we get a wavelength of 531.3 nanometers. It should be 532. I'm pretty happy about that. One more check. Let's check with the blue-purple laser, which should have a wavelength of 405 nanometers. Looks like it's significantly closer. So the central fringe is 8, and it goes to 15 centimeters on the side.
So here's the verification with the blue laser. We calculate a wavelength of 413.2 nanometers. Should be 405 nanometers. So anyway, the different colors of light behave pretty differently in these optics. And it's nice that since the optics are constant, we can use one wavelength of light to find out about the optics and then make predictions about others.
So in summary on this video, we know that because there's diffraction patterns through optics like double slits and diffraction gratings, that light acts kind of as a wave. It behaves just as the water waves did at the beginning of this video. We used one laser with a diffraction grating and a known wavelength to figure out how far spaced apart the slits in the diffraction grating were. We then verified this calculation by looking at two other lasers of known wavelength. What you guys will do in class as a lab is I'll give you other lasers and I'll ask you to determine their wavelength using what we found out in this video.